Welcome to the General Chemistry 1 class. This section is on the electronic structure of atoms, focusing on orbital diagrams. In this lesson, we will draw an orbital diagram to represent the electron configuration of atoms. The electron configuration can also be expressed using orbital diagram, which consists of blanks or boxes as the orbitals and arrows as electrons. In making orbital diagrams, there must be a clear distinction between orbitals of each subshells and orbitals of different shells or subshells. As you can see on the diagram, there is a difference between the orbitals of different subshells and the orbitals of the same subshell. Orbitals in a subshell have the respective m1 values. For this lesson, we will disregard these values as orbitals in a subshell are of equal energy. Recall the rules to consider in writing electron configurations. First, Aufbau principle. Second, Pauli exclusion principle. And third, Hund's rule. We will use orbital diagrams to illustrate these rules. First, Aufbau principle. Recall that electrons fill first the orbitals with the lowest energy before those with higher energy levels. Subshells must be filled with electrons according to the following sequence: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. Note that all orbitals within each subshell must be completely filled with electrons before the next subshell is occupied. When the electron has a spin-up orientation, the orbital diagram must consist of an arrow pointed upward, while when it is at spin-down orientation, the arrow in the diagram must be pointed downward. Now, let us make a convention in this lesson that the first entering electron in an orbital or subshell must be in spin-up orientation. As an electron enters a subshell with degenerate orbitals, the electron may start filling any of these orbitals as they all have the same energy. However, as our convention, filling of electrons starts from the leftmost orbital going to the rightmost orbital of every subshell. Second is Pauli exclusion principle. Recall that in Pauli exclusion principle, no two electrons can have the same set of the four quantum numbers. Consider helium Z is equals to 2, an element with 2 electrons. In the ground state, the 2 electrons occupy the 1s orbital, suggesting that they have the same values for N, L, and Ml. In accordance with the Pauli exclusion principle, these 2 electrons must have different ms values. Thus, they must have opposite spins. Then the last one is the Hund's rule. This rule can be stated in different ways. Some are as follows. 1. The orbitals in a subshell must be filled singly with electrons of parallel same spin before being completely filled up with electrons of the opposite spin. Or, a subshell must be filled with electrons in such a way that the number of unpaired electrons is maximized. Electrons conforming this rule minimize repulsive forces between electrons, thus lowering the energy. Take note that as a convention, orbitals will be filled first with electrons that are in spin-up orientation. When all orbitals within a subshell are half-filled with electrons, then they can be paired electrons having spin-down orientation. In the presence of an electron in a subshell, the second entering electron must occupy another orbital of the same subshell. Moreover, it must be of the same spin with the other electron. The third electron occupies the remaining vacant orbitals in order to maximize the number of unpaired electrons. The fourth electron can fill any of the half-filled orbitals. Its spin must be opposite to the other electron in the orbital. The fifth and sixth electrons must fill the other orbitals with the same spin as the fourth electron. Recall that expanded electron configuration is used to show how electrons, usually the valence electrons, fill each of the degenerate orbitals in a certain subshell. It can be seen on the orbital diagram of neon that the 2s and 2p subshells are completely filled. For sulfur, the 3p subshell consists of 4 electrons. In order to obey the rules for minimizing the energy, only one orbital must be occupied with 2 electrons, while each of the other 2 orbitals have an unpaired electron. Recall that chromium was discussed in a previous lesson to have an electron configuration that does not obey the rules for writing such. Again, the discrepancy can be attributed to the stability brought about by the half-filled 3D subshell. Another anomalous case discussed in a previous lesson is that of copper, in which the observed electron configuration prefers the migration of a 4s electron into the 3D orbital with unpaired electron as driven by the stability of completely filled 3D subshell. Orbital diagram helps us understand the concept of diamagnetism and paramagnetism. An element or ion is diamagnetic if all subshells in its electron configuration are completely filled. When all subshells are completely filled with electrons, all orbitals consist of paired electrons of opposite spin, leading to zero net magnetic field. On the other hand, an element or ion is paramagnetic when there is at least one subshells in the electron configuration that is not completely filled. At least one orbital contains unpaired electron. The presence one or more unpaired electrons give magnetic effect to the atom or ion. So, to summarize, elements can be classified based on their magnetic properties as diamagnetic or paramagnetic. Based on the electron configuration, an element is diamagnetic when all subshells are completely filled with electrons. If not, the element is paramagnetic. So here are the references or bibliography for this lesson. Thank you for watching and have a good day.